Hello, everyone, and welcome to our media briefing today for the James Webb Space Telescope, an international mission led by NASA with our partners, the European Space Agency and the Canadian Space Agency. My name is Elise Fisher. I'm with NASA's Office of Communications, and we are here live today from NASA's Goddard Space Flight Center in Greenbelt, Maryland, where we have just released the full set of the first full-color images and spectroscopic data from the Webb mission. So we have a panel of experts here to answer your questions today about the images and the data that you've just seen, as well as what that means for Webb's ability to explore the unknown in our universe. But first, I would like to turn it over to Eric Smith, Webb's program scientist and chief scientist of our astrophysics division at NASA headquarters, for some opening thoughts.
Thanks, Elise. Well, this morning we saw the amazing data that Webb has given us. We certainly thank all the scientists and engineers who have spent decades developing this amazing machine. It is now the science community that must take this unbelievable instrument we have been given and turn it into knowledge. Another thing you probably got out of this morning's briefing was that there are discoveries in these data, and because they were more or less practice runs with the instruments, we're making discoveries and we really haven't even started trying yet. So the promise of this telescope is amazing. And of course, as Elise said, we couldn't have done this at NASA without our partners in the European Space Agency and the Canadian Space Agency. I want to thank the scientists who have been supportive and patient for the many years that it has taken us to put Webb together. I know you will be happy with the results that you get out of it. Equally important, this is a telescope for the world, and that's why we want to have you part of the story that we tell everyone. It's important to get this out. The world's vehicle for deepest space exploration is open for business. All aboard.
Thank you, Eric. So with that, we will begin to take questions, and I'd like to introduce our panelists who are here to address them. In addition to Eric Smith, we have Nicole Colon, Webb Deputy Project Scientist for Exoplanet Science here at NASA Goddard. We have Christopher Evans, Webb Project Scientist for the European Space Agency. Klaus Pontoppidan, Webb Project Scientist for the Space Telescope Science Institute. We have Renee Dayon, Principal Investigator for the Near Infrared Imager and Slitless Spectrograph, or NIRISS instrument, aboard Webb with the University of Montreal. We have Amber Strawn, Webb's Deputy Project Scientist for Communications here at NASA Goddard. And finally, Jane Rigby, Webb Operations Project Scientist, also here at NASA Goddard. So we are going to take questions today, both here in the room as well as from media who are on the phone lines calling in from around the world. So we have two members of our team who will, if you raise your hand, provide a microphone for you to ask your question. And we'd ask that when you do so, you please let us know your name and your outlet as well. And if you do know which member of the panel you'd like to direct that to, please feel free to note that as well. So let's start with some questions here in the room.
Thank you. Seth Borenstein, the Associated Press. Two questions, if you don't mind. First, for Nicole, for the average person who sort of was hoping to see a picture of an exoplanet, instead we see the spectrum. Can you tell us why that is so interesting and important? Why is that better than a picture, and what does it tell you? And for Eric, if we go back to last night's deep field image, or someone else's better, prefers to answer this. I know, is it too early? It's too early to say how far back this shows. Can you give us a range, since you're saying this is further and deeper? I mean, I keep hearing more than 13 billion, but you've had more than 13 billion before. So where are we looking? Are we looking at 500 or 600 billion after, 500, 600 million after the Big Bang, or what? And thank you.
Sure.
So with the exoplanet transit spectrum that we released today, which came out of NEAREST instrument, which Renee Doyon is a PI of, so I just want to make sure we acknowledge him as well. That spectrum is definitely an indirect method, right, of how we study exoplanets. And the thing is, compared to direct imaging, so Webb will also do direct imaging and take some pictures of known planets, and it will also search for as yet undiscovered planets with direct imaging. But in this case, we know that at least for cycle 1 observations, the first year of science, transit observations are a heavy part of the science program. So this first image or spectrum really represents what the community has proposed so far. And a lot of the direct imaging capabilities, though, they'll be demonstrated over the next year, and then that will also be a big part of Webb's story moving forward.
I'll start on the deep field question, and then I'm going to toss it over to Jane, who's the real expert on that. We know from taking spectra in that field that there's at least one object that is 13.1 billion years, that's how long the light has taken to get to us. So we know from other data, Hubble and whatnot, that we can see a little bit past that, 13.4, 13.5. So what this tells me, though, is that Webb, again, practicing with Webb, we almost got there to what Webb was built for. So when we do a program specifically designed to look for those farthest objects, we will get there. And I'll let Jane elaborate.
That's most of it. Yeah, so the spectroscopic redshifts that we got in that field include a redshift 8.5, so that's the look-back time of 13.1 billion years. And what's remarkable is just how good the spectra are without long integrations. You just, okay, there you go. We're used to barely being able to tell the redshift, and instead we have a spectrum that has so many lines, you can say, I can tell you how many oxygen atoms there are in that galaxy. And so, yes, it's not the record holder because we're just getting started. This is the proof that it works, and that when we take these kinds of data, it goes really deep. As far as deeper images than the UDF, that's based on examining the images and figuring out what is the deepest, what's the faintest blob that we're seeing. And we're confident that that's deeper than images that Hubble has taken in the same wavelengths. I mean, honestly, it's not hard to do that. A couple of hours and you beat Hubble in those wavelengths.
Just to follow on from Jane, so we've seen one of the first spectra was shown in the broadcast, and you'll see in the products that we've actually used the near spectrograph, the multi-object capability. So we have this deep field taken with NIRCam, and we can use the near-spec multi-object spectrograph that was one of the ESA deliverables to observe more than one galaxy at a time. So we can really make the most of this precious observing time. And I think there was 48 in that first test. And again, we'll be doing this, following up these deep fields with this capability to get the spectra of tens of galaxies each time. And those lines just pop right out, and you can do things we couldn't imagine of just last week. So.
If I may add, this target is very special because it was observed by all 4 science instruments. For example, NEAREST has a mode to do, like NearSpec, to take spectra, but in this case it takes spectra of everything with slightly less sensitivity, but instead of a few tens of objects you can observe, there's thousands of objects in one shot you can observe. And so, so this galaxy clusters represent this very tight and strong synergy for all 4 science instruments working together to answer one fundamental question, the origin of the universe.
Great, thank you all. We can take another question here in the room.
Hi, this is Issam Ahmed from AFP. Maybe for Eric, 2 questions. Maybe the first one is, or for Amber, I'm not sure. Are there any interesting scientific questions thrown up from the practice images we've seen so far? Are there any kind of lines of investigation that you would want to pursue on the basis of what we've just seen? And the second question, maybe, I don't know, Klaus, just for the public's knowledge, how long does it take to sort of process these spectacular images from infrared into these kind of really colorful, beautiful photos we see, and what does that involve? Thank you.
Okay, I'm going to let Amber go ahead and take that one.
Sure. So with the deep image, of course, the first thing we think about are those very, very distant galaxies, like Jane describes them, the rubies, scattered across that image. I study star-forming properties in sort of intermediate redshift galaxies and also galaxy morphologies. And for me, the first thing that stood out about that image, in addition to the little red dots, which are great, but was just the astounding detail that you can see in some of these galaxies. You can see star-forming regions in what are almost certainly, very distant galaxies, and they just pop out. There's just so much more detail. It's like, we've used this kind of corny acronym, but it's like seeing in high def, right? And just the detailed morphology structures that we see in this image it's fantastic.
All right, so I can answer the other question. So I think on average we spend probably a couple of weeks on each image end to end, from actually getting the data on the telescope, downloading them, and then processing them through this whole process before we got what you see on the screen there. There's a lot of stuff involved, and in some way we know that we're sort of the first science users, like the first people who had to actually take data from the telescope and create a product that you can do science with, or that is such high quality. If you look at the images, but also when you zoom in on it, and you zoom in and you look at details, that every detail you see is going to be real. And I just wanted to highlight as well for the near-spec spectra that we have seen, those amazing spectra that others have talked about. Those were only taken at the very end of June. So in that case, we only had a few days to get those spectra. So this is still a testament for how powerful this observatory is, that you can get the quality of data that you can turn around. For the first time, we're doing this for science, right? In just a few days.
Hey, thanks a lot, guys. Bill Horowitz, CBS News, and this, I'm not sure who to ask this, maybe Jane or Amber. Can you talk about when you saw the actual data and your impressions or your anticipation going in? What I'm trying to understand your reactions as both astronomers and human beings to seeing this thing turn this dream into reality for you. In other words, did it match that? Did the reality match the dream? Do you view this as an incremental step forward for astronomy, or is it, the kind of revolutionary step that Hubble was back in its day? Can y'all just give us a little perspective on? Well, anyway, you got it. You
Sure.
get what I'm saying.
Okay. Let me take that. Okay. So I'm one of the 3 commissioning scientists, so I've seen a lot, maybe most of the data that's come down during the 6-month commissioning period. And I will say that for me, earlier than this, that the first focused images that we took, where they were razor sharp, that for me was the one where I had the very emotional reaction of, oh my goodness, it works. And it works better than we thought. And shortly after that, we got a standard star so we could measure how much light was going through the telescope. And that's not pretty, it's just a star, but like, oh my gosh, it really does work. And so for me, definitely it was I think personally, I went and had an ugly cry. Okay, because it works. What the engineers have done to build this thing, it is amazing. We have an amazing engineering team, and across the board, we beat spec. Some of those engineers are in this room right now, Mike Menzel and his team. They beat spec again and again and again. So I will say, first, it was a combination of giddy in the room, looking at the data, oh my God, this is great, and then going and having a little sob because it works. As far as what does this mean, the first thing I did when I came on this project 11 years ago was I made a plot of how deep does this telescope supposed to go versus what does everybody else do? And because nobody had made that plot, I was like, I'm just trying to wrap my head around it. I was like, oh my gosh, we're 2 orders of magnitude more sensitive than other telescopes. And it goes to 3, right? Okay, how could you not discover stuff if you're 100 times more powerful than previous telescopes? So from the data that I've seen so far, from the work that we've seen in commissioning, which is all commissioning data, and then this first week of science, yeah, this is going to be revolutionary. These are incredible capabilities that we've never had before.
If I can pick up on this. Yeah, I'm also I'm part of the commissioning team as PI at the FGS and nearest instrument provided by CSA. And, I'm a scientist, so I've been working on this project for 20 years, so we should expect what we saw. But no, several times in the last 6 months, I nearly break my jaw of what I saw. these incredible images and the first transiting exoplanet spectrum in front of me, coming right out of the box of the data. It was just amazing. And so, and I think our fellow scientists will feel the same thing when they look at the data. These data are just amazing. I think it's fair to say that today we're turning the page. It's a cliche, but it's true. We're turning the page on several new chapters on exoplanet, atmosphere, the early universe, star formation, you name it. And we don't even know what we're going to find. It's exciting.
We can take another question in the room here.
Thanks. Jeff Faust of Space News. I know the early release observations are designed to showcase the broad scope of what JWST can do, and I know one of the important areas of science for JWST is solar system science. So when can we expect the first solar system images or spectra from JWST?
Well, so there have already been solar system observations taken, and so those observations will be released, I think, on Thursday, along with the rest of the commissioning data. So that's when the public will see the first ones. And we're very keenly aware that this is an important science area for the observatory. We also very confident that we know that we can produce wonderful, beautiful data and images for this. And so I have no doubt that we're going to see spectacular things from the solar system soon. It was just an early decision made for the early release observations that we didn't want to have to count on the moving target observations working with it, keeping things not too complicated. As it actually turns out, we probably could have done it, but here we are. Sure.
We will come back to questions in the room in a moment, but we actually on the phone lines have media who are live at the Canadian Space Agency headquarters in Quebec. And so we have some media questions on the line that we can go to now. So I'd like to ask our operator to please provide instructions for our phone media to ask questions and take our first question there.
If you'd like to ask a question at this time, please press *1 and clearly record your first and last name for your question to be introduced. Again, that is *1. One moment, please. Our first question comes from Kenneth King with New York Times. Your line is now open.
Hi, thank you. I was wondering, when will the first-year program observations begin? And can you tell us who's going to be first?
Klaus, go ahead.
So the first year of science observations have already begun. We have already taken data for scientists to one time in the first year. And those data will be released to the principal investigators of those programs in the next day or two. And some of them are public, actually, so it will be released to the world as well. So there's another batch of data there, and we're just going full steam ahead. What are the first ones? It's actually various different first ones there. There are more deep field data, for example. So that's very exciting. From a program called SEERS, which looks at wider regions. Remember that the deep field we have here is a very small region that goes deep, but many of the programs, they are looking at observing many more galaxies, many thousands in a wider area of the sky. So there's some of that. And you can go to our website as well and look up what observations are being taken every week. So there's a schedule published there.
Thank you, Klaus. We can take another question from the phone as well now.
Okay, our next question comes from Andrea Matt with the Canadian Space Agency. Your line is now open.
Thank you. This is a question from Raymond Fournier from the Agence Science Presse in Canada for René Doyon. We know the rate of expansion of the universe through Hubble images. Will Webb redefine this?
Okay, we don't expect Webb to focus on that, and Webb will very focus on the early universe. I mean, you've seen this deep image, and we don't expect Webb to But who knows whether, I mean, that's maybe a question for James to answer.
I think the main way that Webb can contribute to understanding the age and the expansion rate of the universe is the nearby part. Is figuring out the distance ladder, the distances to Cepheid stars and red giant stars in nearby galaxies. That's what sets that ladder that walks out into cosmological scales. And dust gets in the way of dust is the largest source of error in many of those measurements. And so there are multiple approved programs in the first year to go observe these standard candle or standardizable stars to understand the distances to nearby galaxies, which then lets us leapfrog out and measure the expansion rate of the universe.
Thank you both. Go ahead, Chris, if you'd like to add.
Just to add to that, coming back to the transformational question earlier. So in Stefan's quintet, you've got the galaxy on the left-hand side, which is slightly closer, NGC 7320. And that's at, 40 million light years. And at the moment, we just can't go and resolve the stellar populations in a galaxy like that. And suddenly in that image, as someone said on the broadcast, you can see the whole populations, you can see the star clusters, you can see evolved luminous red supergiants, AGB stars that are producing dust. And then we can go and look in these galaxies out to these tens of millions of light years to do the work that James was just mentioning, to build that ladder in a way that if you try and do this with Hubble, it's just not sensitive enough. If you try and do it from the ground, you can't get out to that distance or the dust is in the way. So it's just, and when you've got the myriad observations as well at longer wavelengths to broaden the wavelength coverage, it's going to be hugely powerful.
We can take one more question from the phone line before we come back to the room here.
Okay, the next question comes from Christopher Kokinos with Astrology Magazine. Your line is now open.
Thank you. Yeah, that's Astronomy Magazine, just to be clear. Yeah, I wish I was in the room to see the reaction. First, congratulations, everybody. Really incredible stuff. And I know that we've heard terms like amazing, revolutionary, exciting, and so forth. I'm actually wondering if one or two of the project scientists can kind of compare the Webb to another moment in the history of astronomy or science. I mean, what do you rank this with? The discovery of DNA, Galileo's first observations of the moon. I mean, where would you sort of rank this in comparison to other breakthroughs in astronomy? Thank you.
So I'll take a first crack at it so everybody else has time to think of a good answer here. For me, it is like seeing Hubble again, but actually better because we have this coverage that overlaps with Hubble, and we're actually even sharper than Hubble there. So this is, again, seeing the universe in a new way that while we expected we could be able to do this, to actually see it for the first time, internalize it, tells me that everything we've planned through cycle one, the astronomical community, was bold, but it wasn't bold enough. So I'm really excited for what people now plan to do for the second cycle, seeing just how capable the facility is. So for me, the closest thing would be Hubble, when it was repaired and we saw everything kind of snap into focus. I don't know about others, Klaus?
Yeah. To me, so I'm not comparing to an astronomy mission, but almost. So one of my favorite pair of missions were the Voyager missions, right? Launched about the time that I was born, still going. And I remember growing up, being a kid and seeing, a few years in between those first high-resolution images of the outer planets. And it's one of the things that brought me into astronomy today. So I think that's what reminds me the most of what Webb is, seeing these things in high resolution for the first time and just going, wow, there is so much there.
I mean, if I may, in a way, we may have to wait several years to answer that question, because history shows very eloquently that whenever a new facility is online and you ask the questions 5-10 years later, what was the biggest discovery of that facility? Well, nobody could predict it. And in fact, we've designed this telescope and instrument to do incredible science that we're going to start executing now. But really, we don't know what we're going to find. Hubble is a good example. Hubble was to measure the Hubble constant, and it did. but nobody anticipated that they would measure a universe that is accelerating. That was a Nobel Prize. So who knows what's coming for JWST, but I'm sure we're going to have a lot of surprises.
Thank you. We can come back to the room now for some questions, and actually maybe not to make you run around, but maybe we can take one in the back there as well.
Hey there, thanks so much. Emily Pandis from NBC News. I have two questions for you. Do you plan to aim Webb at one of our local planets like Jupiter, and what do you expect to see? And our closest known exoplanet that we could possibly live on, it's only 4.2 light years away, so it's too far to travel to, but could you imagine its surface at that distance? And we'd love to hear about any plans you have for possibly habitable worlds.
Oh, go ahead, Jane.
Sure.
I'll take the Jupiter one. We've already pointed at Jupiter. You're actually sitting next to Begonia Vilo, who is part of why we can point at Jupiter. So one of our commissioning tests was to check that we can do moving targets, right? That we can track something moving in our solar system. We had a speed limit of 30, which is as fast as Mars can get. We actually broke through that. We managed to get a speed limit of 67. So we can track faster targets than we promised because the guider works so great. For Jupiter, we did a test of Jupiter just because Jupiter is so bright that it can be challenging to guide on it and look at the faint things like its moons. But we did that test during commissioning, and it worked, and the data are in the archive. And so there are programs in the first year of science, peer-reviewed approved programs, to study Jupiter and the Jovian system that we now are confident will execute. And then that initial data, which is just a couple seconds to prove, okay, yes, we can track Jupiter as it moves, those will go live in the archive later this week.
And those Jupiter images are beautiful.
So nice. They made me very happy.
Great, thank you. And maybe Nicole, Renee, if you want to take the question about exoplanets as well.
Sure, yeah. So I can start. So for the closest exoplanet system to us, that one doesn't transit its star. So that's one of the main ways that Webb will be studying exoplanets. So we can't, at the moment, use Webb to study that exoplanet system. However, speaking of, you mentioned potentially habitable planets, we did a countdown with TRAPPIST-1 earlier. Webb will be observing every single planet in the TRAPPIST-1 system. So there's 7 planets, and several of those are considered to be in the habitable zone of that star, which means they have the right temperature that they could have liquid water on their surface. What Webb is going to do is first check whether they have an atmosphere at all. That's our first step in the process. And then check, okay, now, if we confirm there's an atmosphere, what can we tell about the composition? So it's a stepwise type of process, but that's our prime opportunity to study some potentially habitable planets around the TRAPPIST-1 star. So yeah, if Renee wants to add anything to that.
Yeah, well, I guess what I can add is that what we've learned so far about exoplanet atmospheres is mostly around gas giants, and mini Neptunes, but we haven't really explored rocky planet. And now we have this rock star system, the TRAPPIST-1 system, as Nicole mentioned, and all 4 science instruments will observe that. Due to the first reconnaissance, as Nicole mentioned, do these planets have an atmosphere, and if so, what it's made of? And if we have a hint of an atmosphere, well, you can be sure the community will, put a lot of time to observe these transits whenever they come around. So that's the focus right now. The first year will be TRAPPIST-1.
Thank you both. We can take another question in the room, right up here.
Thank you. Can you hear me okay? Yeah. Asa Stahl, Science News. I have 2 pretty closely related exoplanet questions for whoever wants to take them. Regarding WASP-96b, my impression was that previously our scientific understanding of that planet was that it was the most cloudless of any that had an atmosphere observed. But JWST sees clouds in the near-infrared or mid-infrared. So what does that mean, and how representative is that of what JWST can do that was previously impossible? And then secondly, going back to kind of habitable zones, astronomers have been guessing for years how capable JWST would actually be at doing this sort of thing. And now you're finding that it defies expectations to some extent. So what kind of bounty can we really expect? How many planets in the habitable zone around even M stars do you think JWST will be able to look for atmospheres around?
Okay, well, there's about right now a handful of habitable zone planet that we can that we can look at. TAPIS-1 is one. But just to give you an idea about the major step forward we're making today, the main reference for exoplanet atmosphere is Hubble, and it's an incredible machine. And Hubble is saying spectra with that kind of visions in terms of wavelength coverage. And Webb certainly will give us, I don't know, I'm going to hit you guys. It's that big, When you combine the wavelength coverage by NIRISS, NIRCam, NIRSpec, and MIRI, then we have certainly access to all possible molecules. You've seen these wiggles, right? Hubble can only see one of those. Now we have a much broader pictures. The other aspect is Hubble is on a low orbit, so it cannot observe a transiting event very continuously. And so you need to have several visits, and that's very inefficient. To obtain this kind of quality data with Hubble would take 10, 15 times more data. So Webb will be absolutely revolutionary in that respect.
Sure, and then I'll add to that. So specifically for WSP-96, again, you mentioned clouds and hazes, right? That hadn't been seen in that atmosphere before. So the benefit of having a space telescope is we get above our atmosphere, right, to look for clouds and hazes in other planet atmospheres. So the original discovery of that it was a clear atmosphere was actually based on some ground-based data. And so now we have kind of the full picture. So the ground-based data covered a part of the optical visible light spectrum. And now we have a better picture pushing into the near-infrared with NIRISS. So we can better understand, okay, what layers in the atmosphere might have clouds, because that's also part of the stories that we're able to tell the structure of the atmosphere, not just what's in it. And then, going to the point of, more habitable zone planets, Webb will, I think the community will encourage Webb to target as many as they can. Part of the problem is it just takes time. We have to observe transits exactly when they happen, and they only happen every so often, especially for a planet in the habitable zone. It can be 5 to 10 days for the smallest star, much longer if you look at Earth. So it takes time. So that's, in some ways, our main limitation is literal telescope time.
Thank you both. We can take another question in the room here.
Thank you. Hi, I'm Marina Corrin with The Atlantic. My first question is probably for Jane and Amber. Can you tell us more about the tiny details that we're seeing in that Carina Nebula image? And then for my second question is for anyone who would like to take it. How does an image like that make you feel?
Sure. So for Carina, a lot of the detailed structure we're seeing is due to these newborn stars, because newborn stars are very energetic. They have these massive stellar winds. And so you see these examples of sort of bubbles and cavities, and that sort of structure is all due to the fact that this is this sort of stellar nursery where these stars are being born. And that image too, sort of like the deep field, it's just, there's so much in it. If you even look like up at the very top of that Carina image, there's like HH objects that are getting blown out of that star that's on top of the ridge. Yeah, on the very top, little green things, you can hardly see them. But it's incredible how much detail is in these images. And we are just getting started, right? This is literally the first look. In the coming weeks and months, scientists will have time to dig into these data and learn more about the detailed physics of what's going on in these types of regions. And I think your second question was about how did we feel? Or how does it make you feel? Yeah. I think all of us are, in some sense, we're just blown away. I am blown away by what I'm seeing here. And my own research, again, relates a little closer to the intermediate redshift galaxies, but just being able to see the detailed structure that we've never seen before. And of course, when the reason we're able to see these very distant galaxies is, of course, due to the infrared. But we're also able to see details in galaxies much further away for that same reason, because the UV light that these stars in very distant galaxies are emitting also gets shifted, to the infrared part of the spectrum. And so, it's incredible to be here, and a lot of us here have worked on this. I think maybe all of us for over a decade at least, and so it's great. It's great to be to this day finally.
If If I may, we're scientists, and these days these images are used to do science. But when I saw that one in particular, I felt I was going into a gallery. This is an art piece, this thing, that was revealed by the telescope, and there's many of them yet to be unveiled. So I think there's a good bridge here to make between science and arts. This is a beautiful image. So it goes beyond my scientific mind here.
And Klaus, did you want to jump in as well?
So I think the Carina Nebula is sort of emblematic of some of the differences that we'll see with Webb compared to what expectations were, in particular in terms of nebula. Right, so those of you who have been following Webb may have seen the pillars of creation. You see the beautiful Webb image, and then you see the very near-infrared image taken with Hubble, where you see through the dust, and the pillars, the cloud itself, they become these kind of wispy things that go away. This is not what we will see with Webb. So the Carina Nebula here, that image was really designed with something else in mind. All the structure you see, all the yellow structure, comes from hydrocarbons. And you'll see this a lot with Webb. So these are large, very large molecules. A lot of people argue they're not really molecules, they're too large, very small dust grains that consist of carbon and hydrogen put together in very complicated structures. And the universe is just full of them everywhere. And we see them to the edge of the universe. What happens here is that they light up when you shine on them with ultraviolet light. And the part of the cloud that lights up is a very thin sheet on top of the cloud. The cloud is filled with them, but it makes you see just the surface. And that's what gives you the three-dimensional structure here. It's this thin surface, almost like a blanket that sort of waves across the field. And so it was designed to show that, but also to highlight how Webb will allow us to understand these hydrocarbons. And you're asking, why are the hydrocarbons important? Well, this may be the way that the universe is transporting carbon, the carbon that we're made of, to planets that may be habitable for life. Because these very stable molecules are very difficult to destroy. They're hardy, and so they make it all the way to planets in the habitable zones.
Go ahead, Eric.
So a lot of people sometimes see pictures of space and they think it makes them feel small. When I see these pictures, they make me feel powerful, that a team of people can make this unbelievable instrument to find out things about the universe revealed here. And just seeing that, pride in the team, but just sort of pride in humanity, that when we want to, we can do that.
And that was always out there, right? The universe was out, it's been out there. We just had to build a telescope to go see what was there. Yeah, very similar feeling of maybe people in a broken world managing to do something right and to see some of the majesty that's out there.
Great, thank you all. We now can go and take a couple questions from the phone again to ensure that those who are dialed in also have the chance to ask their questions. So I'd ask the operator to please, again, prompt for questions on the phone and take a couple more from the phone lines.
As a reminder, if you'd like to ask a question, please press *1. Again, that is *1. Our next question comes from Matt Kaplan with Planetary Radio. Your line is now open.
Thank you, everyone. Magnificent images, magnificent day. With the WASP 96b spectra in hand, what are you now expecting, or at least hoping for, in spectra from more Earth-like worlds? I mean, how close might we come to detection of those atmospheric components that could indicate life, biological activity?
Thank you for the question. Maybe Nicole, Renee, if you'd like to start.
Sure, yeah, I can start. So what you've seen with WASP 96 were prominent water vapor absorption features. So those bumps upward actually indicate there's water in the atmosphere absorbing starlight. And so it's very similar as we push towards smaller planets. We mentioned the TRAPPIST-1 planets in particular. These are the best targets right now that are small, rocky, Earth size, with a few of those planets in that system in the habitable zone of their star. We're also going to be looking for evidence of water, and as well as other molecules that contain carbon and hydrogen. So that's methane, carbon dioxide, molecules like that. When you combine all that together, you can understand the content of the carbon, oxygen, hydrogen, and that's important because those are some of the basic building blocks of life. So we're hopeful that we'll see those data come out and reveal the spectra of those atmospheres. And I think we'll just have to wait for time to reveal the story. And then Renee, if you would like to add.
Yeah, I just want to add that of course, we're looking at the system that we know now, but you can expect many more exoplanet systems to be unveiled, and there's, the test missions are already finding a lot. One thing that it is predicted to exist, these water worlds, planets that have a rocky core with thick oceans around them. And the only way to unveil the system is to detect the water features in their atmosphere. And you can expect Webb to be able to do this once we have a target that it looks like a water world. So yeah, there's many new discoveries that we can expect, but focus on relatively small planets. And the majority of them will be around M dwarfs, these very small stars, because it's just much easier to detect the atmosphere around these small stars.
Thank you both. We can take another question from the phone lines as well.
Our next question comes from Ken Kramer with Space Up Close. Your line is now open.
Oh, wow. Thank you. Well, congratulations on all your hard work and the great success here. I'm really interested in the exoplanets, but let me ask you about WASP. I wonder if you talked about the water vapor, but have you detected anything else? Any oxygen, any ammonia, any hydrocarbons? Are you still working on that? What do you hope more to see out of that? Thank you.
So this was definitely, the first look, right? These data have hardly been analyzed. So this is kind of what comes out of the box. And so there's a best fit model that's shown on the first spectrum here. But you could see without the model by eye, right, the features that are due to water. The model is, we call it a best fit model, but it's barely scratching the surface of what we're going to learn. We are expecting to learn really precise water abundance constraints. So not just detecting that there's water in the atmosphere, but how much water is there and the implications for the overall composition. And along with improving the models, because these images, again, were just early release, not detailed, studied in depth yet by scientists, that when you add more to the model, you can understand and pull out, as you're asking, whether there's ammonia or other features. Methane, carbon dioxide are two of the other ones that we would expect in this wavelength range as well. So I think we'll just have to wait for scientists to get at the data and go, work it with their models to learn more.
Just add to that, so Nicole is right? So this is the first shot at actually getting an exoplanet spectrum with Webb. So one thing is the model, right? But when you're looking at the kind of precision we have here, 100 parts per million, you're into a regime where you're depending on details of how the instrument works, how the detector works. And so I think there will be, even of this spectrum, once the experts get a chance to look at the raw data, they'll be able to take out some of those systematics that are in there and produce an even better spectrum, even with the data we have here, in addition to more data we'll get. So in that sense, this is also only the beginning.
Yeah, if I may add, so what is game changer here is the ability to probe several molecules. Hubble was mostly focused on water because of its narrow view, as Nicole mentioned here. Potentially one could detect methane in the spectrum, also CO. The fact that we don't see it very loudly means that it's not there. But as Nicole mentioned, this is not just a demonstration. This is scientifically useful data that people in 2 days will just jump on it to analyze. And then people will want to get other observations with NIRSPEC and MIRI to get the broader picture about the chemical composition of this atmosphere.
Okay, thank you. We can come back to the room for some questions as well. I know there were a few more up here. Go ahead.
Hi, I'm Rebecca Sohn from space.com. I had two questions. My first is for anyone who wants to answer. I know you keep saying that, in the coming days and weeks and in the next year, people will analyze these first images and others and sort of find out more. Do you have a favorite sort of expectation that you're hoping to find out more about just these first images? And my other question is specifically for Eric. Now that sort of the first images have been released with this telescope, I know that a lot of people are sort of not satisfied with the name James Webb because of his association with discrimination against LGBT people. I wanted to ask if the sort of name is sort of a done deal.
Because the latest there is that if you've been following, our historians have gone back to conduct some additional research in archives that were recently reopened after they'd been previously closed due to COVID-19. So they are compiling that research into an update that we'll be looking to share soon, but I'm happy to follow up with you on that statement after the fact. And I think your other question was about excitement for the coming year in terms of what targets might be coming up. I don't know if there's anyone who wants to
Specifically with these first images, like what are you hoping to find out with sort of further analysis?
Who wants to jump in? Go ahead, Chris.
So they didn't have time to necessarily show it earlier. In Stefan's quintet, there was a lot of excitement immediately after the broadcast of the spectroscopy in there as well. So we've got an integral field unit in both NIRSpec and the MIRI instruments where you can slice up the spectra and scan through in wavelength. And they managed to get observations of the AGN there, right in that northern galaxy, where you can see just the gas kind of coming off of that supermassive black hole at high velocity. You can see that dynamics in the different lines going through. So we can learn about the excitement of that gas, the chemical properties of that gas. So you can see here in the emission lines on the graphic. And then you can see the sight line as well into the region kind of around the central supermassive black hole for the first time. And so we think the mass of this black hole here, it's a few times more massive than the mass at the black hole at the center of the Milky Way. And then there was another plot where you can start to see the velocities of that gas. So on this one, so at the bottom there, plus or minus 200, doesn't sound a lot if you see kilometers, but that's per second. So if you think of that in miles per hour, these are tremendously powerful jets coming out of this AGN. This is kind of to the moon and back in an hour. And we can learn about the processes in this gas and what's happening around the black hole for the first time by the power of this spectroscopy. And that's just, I think, going to be a real huge, exciting leap forward.
Is it true, Chris, that the power of those outflows from the AGN, they have enough power to disrupt the whole galaxy, right, to change the rate it forms stars and so on?
So yeah, we get this process called feedback, where that then, in the same way as we're looking in Carina, where you've got that ionization coming and triggering star formation or influencing star formation, we can then look at the feedback of this huge powerful outflow from this galaxy and the impact that has on the environs there as well. And then you can also see the molecular gas further in around the central black hole.
Yeah, if I may, this data set is so rich. As I said, it was observed by all 4 science instruments, and the nearest instrument actually got a shot of taking spectra of everything. And what we see there is there's a background galaxy that is with lots of distortion. And in fact, this is the same galaxy appearing twice in the image. But when you look at the image, you don't really know that it is the case. But by taking a spectrum of it, actually, we have proved that this is the one, this is another one. It shows that these 2 arcs are exactly the same galaxies. And that was worth 3/4 of an hour worth of observations. So it's just amazing. It's as Jane said this morning, you take that data before breakfast. And we're going to get much more of that in the coming years. Again, all these images represent 120 hours. Well, there's 6,000-7,000 worth of time in a year after year. So it's an incredible amount of data that will come down.
And I think it's also important to note that just like with Hubble, these data, a lot of programs do have proprietary time, a 12-month proprietary time for the PI. But then after that, it's all public in the archive. And a lot of the data actually in the first 6 months of this mission will be public immediately, including these early release science programs, some of which have already been taken that you've heard. And so this is data, this is a telescope for the world, for scientists everywhere to be able to start to dig in very soon and do real science with this data.
Great, thank you all. We can take another question from the room. So we have some over here.
Thank you so much, Joel Achenbach with the Washington Post. To follow up something Marina asked earlier, to explain the Carina Nebula. Can we look at the Southern Ring Nebula, and can someone explain a little more about what is going on there? What is the story of that dying star? Why is it dying? Are we sad about the star dying? Apparently there are two stars, not one star. It looks like a nice swimming hole in space. It's a beautiful image, but we need the story maybe a little bit more if someone could do that. Thank you.
Yeah, so what you have here is a star that's dying. It's not just any star. This is a star that is much like the sun, or at least like the sun will be in 5 billion years when the sun dies. So what happens here is that when stars like the sun die like this by pushing out their outer layers, is that they essentially seed the galaxy with elements like carbon and oxygen, and that's where a lot of the carbon oxygen comes from. Actually, we're made of. So there's a life cycle of stars, right? So this is the end for this star, but it's the beginning for other stars and for other planetary systems. So the carbon and oxygen and other elements that this puts out will eventually end up creating planets somewhere else in the future. So I think that's really the basic story here. And what Webb allows us to do is to understand that in much greater detail. What you'll see when you zoom in on this picture, for example, is the turbulence of the flow. There's so many clumps and structure in that, and that tells you something about how the star manages to push out its outer layers. You know, how that physics works, so we can understand how many of the elements actually come from this type of object. We can also measure, how much of the elements. And in this case here, it probably creates some of these hydrocarbons I talked about earlier that you see in the Carina Nebula, hardy carbon-bearing molecules that again ends up in planetary systems. So by understanding the formation, again, we'll understand why there are so many in the universe, seeing to the edge of the universe. So it's really understanding where we come from that is in this story.
Thank you. I think we had some other questions over here as well. Go ahead.
Hi, Brandon Lewis with the NASA Social. I think a common question many people would wonder is this actually how it looks? And with a broader spectrum of light being captured than Hubble, how do you go about deciding which color channel to assign in the RGB color spectrum? And how would that look compared to how we actually see it?
Thanks for the question. Who would like to jump in on that one? Klaus again?
All right, so the color images here are created using infrared colors. And I just want to emphasize that infrared colors are just as real as visible colors. In fact, there are more infrared colors than there are visible colors. Just because our eyes can't see them doesn't make them colors. And so if you look at the electromagnetic spectrum, the visible light, we can see it's just this tiny sliver of the whole electromagnetic spectrum. So what we do with Webb is not making up colors. Or doing something odd with them. Like for example, we use what's called chromatic order. So we assign to the blue color an infrared color that is bluer, that means has shorter wavelength than a red color. And so we always maintain that order. Blue color means shorter wavelength, red color means longer wavelength in these images. And so you can think of it much more as a translation of a language you don't understand. Right? So you take the light and these colors, you translate it into the visible spectrum. So that if you had infrared eyes that were sensitive to this light, this may be what you would see. And there's no difference in the reality of this compared to the reality of the visible images you see with Hubble.
Okay, thank you.
If you had 6.5 meter diameter eyes in the infrared, this is what you would say.
All right, great. It looks like we have another question from here in the room.
Hello. Yes, my name is Kevin McLeod, and I'm from NASA Social. I'm also the curator of Deaf Eyes to the Sky. I have a question from my group. Just what was your priority in the observations from this week, in this coming week? What are your priorities in the observations?
Okay, thank you. I was going to say for EROs, or feel free to jump in, Eric.
Yeah, well, as we talked about earlier today, they are executing normal science. And so those are priority order assigned by where the telescope was in the sky, what was visible, which instruments were ready at the time the observation came up. So those are going on right now. ERO priority was picked essentially on beauty and how informative and how interesting the science story was for each of those. And if Klaus can give you more detail on how they were individually picked, if you want to.
So ERO, the targets here were really picked for the, as Eric said, for their potential for making beautiful images, but not just beautiful images, but also beautiful images that highlight something different about Webb. Right, so that's why we pick a star-forming region. The star-forming region is beautiful, but we knew that we'd also be able to see new stars poke through all that dust because we used the infrared light. For the exoplanet, it was picked because we knew it would have strong features so that we had a high chance of detecting, say, water in this case here, and show this in a beautiful way. And so that sort of went through all of that. And then, of course, the targets had to be visible at the time that they were observed. And so that made the final down select. Let me just add for the science programs that we're going to do in the next year, there's really no priority in them. They're prioritized based on the schedule. So we don't waste telescope time by going from one part of the sky to a completely different part of the sky, because it takes a lot of time to move the telescope. So they're scheduled according to schedule efficiency. With the one exception is that there is a program called the Early Release Science Program, which is about 500 hours that was selected a couple of years ago. So this is very different than the early release observations. This is a peer-reviewed, ERS, peer-reviewed program made by the community. But the point of that is to make sure that there's even more data available from all the instruments and all the modes, spanning a wide range of science that is public immediately, has no exclusive access, period. And so they get priority because we want the community to have as much data available, in particular by the time they get to propose again, right? So think about this. We're going to have another call for observing proposals from astronomers at the end or of this year, early next year. And I'm very curious about, after people have seen this data, what we're going to get in terms of proposals. And so we don't want anybody to have special abilities to write proposals because they have had access to data that others haven't had. So we want to make sure that everybody in the community has had access to data so they can base their new proposals on that data.
Great, thank you. Let's go back to the phone lines now, as we do have a couple of questions waiting there as well. So I'd ask the operator to jump back in.
As a reminder, if you'd like to ask a question, please press star 1. Our next question comes from Liz Cruzy with Mercury Magazine. Your line is now open.
Great, thank you. Thank you for taking time to answer our questions today. So someone earlier, and I apologize that I don't recall who it was, said that cycle 1 proposals and observations, it turned out, aren't bold enough. So my question is, what would you like to see? How can you push JWST's capabilities further, or as far as they can go?
So I accuse the community of being timid on cycle 1. And I don't mean that they weren't thinking to use a new capability that they had with that Webb was going to bring online. But of course, they couldn't know just how good Webb was going to be when they wrote those proposals. So there's probably some conservatism built into the number of targets they wanted, or how long they think they might have to expose, and so they won't get as many targets because it's going to take longer. And now what they'll see, and when they can have access to these data, is that they can expose shorter in some cases. They can have more targets, or they can go deeper than they thought. So I think round 2, as was alluded to there by Klaus, people will be much more adventurous because they now know just how good the facility is.
Okay, thank you. We can go back, take another question from the phone here.
Our next question comes from Dana McKenzie with Knowable Magazine. Your line is now open.
Hello, thank you. I want to ask again about the Southern Ring Nebula images. So I guess I'd be interested in if you could contrast what you can see in these images compared to what you could see from Hubble. Are there things that you can now spot that you couldn't before? And in particular in the news release, it talked about seeing separate shells around the nebula. And I was wondering if you could see these before or not, and how many shells are there, and what does that tell us about the history of this particular nebula?
Go ahead again, Chris.
I can see. All right, so there were a couple of questions there. First of all, what do we see that Hubble doesn't see? I think there's a key thing we see with Webb, and this goes beyond the Southern Ring as well, is that Webb sees molecules, it sees chemistry. Like Hubble mostly sees atomic gas. What you're looking at is different energies, different temperatures. So Hubble sees the very hot stuff, Webb sees the colder stuff, and this is where you transform the gas from this hot atomic gas to one that creates molecules. And as I alluded to earlier, the molecules become important because this helps material transition through the interstellar medium to new stars and new planets. And so you see all the red stuff there in the Webb image is molecules that you just didn't see with Hubble. Yeah, you do see a number of those shells here. I've just counted them by eye. I mean, anybody can do that. As far as I got with it, right? There's probably a handful of those, and those come from as the star was dying, in its last dying throes, it starts to shake, it pulsates, right? And then at the end of that, poof, it comes out. So you see what the star did just before it created this planetary nebula. I find it fascinating because it's like geological layers, and you can see the history of its last moments.
Yeah, if I may add, you mentioned colors and molecules that Hubble cannot see, but more fundamentally, it's the sharpness of the images. This is the bigger your telescope is, the sharper your images are. And here, this is 3 times Hubble, so we can see much more details of everything we observe with Webb, and that's a big difference.
And Chris, if you'd like to jump into.
Just very quickly, if you just do this comparison, you can see the longer wavelengths with Miri, that hidden star just pops straight out. You've got the dust-obscured white dwarf in there. We can really then look at kind of how the binaries influenced the different structures that Klaus was just talking about. And it's by having that long wavelength for the first time with this fidelity and sensitivity that you just pop straight out, and then we can kind of try and reconstruct the history of it and the different layers. So.
Yeah, and it's a wavelength reach of that, right? Because again, we can see so many infrared colors, and that allows us to see so much more physics and chemistry at the same time with the same telescope.
Great, thank you. Then let's go back to the phone for one more question before we come to the room again.
Next question comes from Matteo Rainey with Physics Magazine. Your line is now open.
Hi, congratulations to everybody. Seeing the richness and the details of these images, I can only imagine what is going to come over the next years or so. I was going to ask about the plan to analyze this massive amount of data, making data public, sort of artificial intelligence kind of analysis and things like that. How are you going to handle this data? Thank you.
All right, so let's see. So we're going to release the raw data for astronomers and planetary scientists from what we saw today tomorrow. That'll open in the archive. And then the next day, today is Tuesday, yes, Thursday, all the commissioning data gets opened up. So that's something like 40 terabytes of data. So everything we've been seeing, that's multiple processings, but everything we've been squinting at, gazing at, wrestling with, trying to make, all of that in commissioning will go public on Thursday. So that's going to be fun. And in fact, I think they're going to do an Amazon, the Institute's doing some stuff to handle the load by putting it on the cloud, figuring everyone's going to grab it. So all of that goes out this week, and it's open for the community. Also for the scientists, we put out a document summarizing the science performance, a very technical document that is available on the Institute's website as well. So That's out today as of 1 o'clock. Yes, so that's out as well. As far as AI, people are going to use lots of different approaches on these data. And I just want to make it clear that this is just the very beginning. This isn't this isn't the kind of press conference where we have a polished result that's taken years of effort, and the effort is the telescope. The telescope works, and these data demonstrate that the telescope works. But the science results are going to be rolling out from here on in. People are going to use lots of different techniques to get as much science as they can out of the data.
Amazon Prime Day is really the 14th.
It's going to be fun to see what the server load is. Yes, I think.
Can I just mention it? So of course, it's not us. It's not us who is going to do all the analysis of this data right there. There are literally thousands of astronomers out there, and we know this because these are the people who are represented even in the first cycle of proposals. And since those proposals were submitted, I'm sure there's lots of new students, lots of new postdocs who are just gearing up to get going on this. So it's thousands of scientists around the world who's going to grab this data and analyze it, and I can't wait to see what they come up with.
And again, just to emphasize, I think this is such a critical aspect of these big NASA missions, is the fact that the data isn't kept, to one or two people or a small team, that it is put out there. I mean, I did most of my dissertation research on archival Hubble data, and it really does fuel the continual innovation that we're able to do in astrophysics because these data are out there on the archive. And so starting tomorrow, again, it's not, we're ready, right? Astronomers are ready for this data. We've been waiting a long time. And so I think, now we've demonstrated that this telescope can do what we set out to do and even better in some cases. And there is a whole world full of astronomers that are eagerly waiting to jump on this data as soon as it's public.
I just want to add that the data processing part is a huge aspect of the project. There are 17 observing modes with Webb, and each require very special treatment. And it's been a lot of effort, years of effort at the Institute within the instrument team to design the best possible data pipeline so that the community can actually use them as soon as they can. And so, as we showed today, it works. And of course, there will be improvement, but that is a very fundamental aspect of the project, that yes, we have a beautiful telescope, instrument that works, but also data pipelines that works.
Thank you all. I know we have a few more questions in the room here. Go ahead.
Thank you. Marcia Smith with spacepolicyonline.com. And I think my question is probably to Eric, but I'd be interested in anybody's answer. And it's one of these philosophical questions, again, about where all this fits in our understanding of the universe. And so you see all these galaxies that you didn't know were there. There are exoplanets everywhere. I don't sense that there are many solar systems like ours, with a couple rocky planets and then some gas giants. They're all different kinds of solar systems. They don't seem to be very much like ours. And I'm just wondering, on a fundamental level, you talked about the scientists being more bolder. Do they need to be bold enough to really ask fundamental questions about whether or not everything we think we know is wrong? Are we on the verge of a Copernican revolution, or we suddenly realize through the eyes of JWST and all the other space telescopes and ground-based telescopes that, we really were missing something in all of our modeling and all of our theories about how the universe works?
So I'm happy to start with that. And I'll pick two specific cases. The distant universe case, the watching the universe turn the lights on, and then I'll talk about exoplanets. So we have seen the surface of last scattering in the cosmic microwave background. We have seen the infant picture of the universe. And with current telescopes, we've gone back to when galaxies were sort of young children. We're missing that evolution in between. And so in those hundreds of millions of years, the universe forms its structure that we know today. We have theories of how that worked, but this is the facility that we can use to test that. This is something we know, and this is what we built Webb to do. So I expect it will be interesting. Will it be transformative? I'm not certain, but it's what we built this thing to do. Now, the general capabilities that are associated with that allow us to do many other things, most of which we probably don't know today. But in exoplanets, which we didn't build this for, we will begin to really do detailed science of the multiplicity of worlds. You're right that our solar system looks unique now, and so with this, we'll begin to say just how unique is the place that we live. Are there other places like it? I think that'll be the first transformational discovery that comes out of Webb, the habitability question that it'll be used to ask.
Go ahead, Chris.
Can we get the image of the deep fields with the near-cam and mirror image? I think, just as an excuse to show this, so this was kind of one of the European contributions was towards the MIRI instrument, but just on the left here you have the deep field with including the MIRI wavelengths and just the colors here and the different galaxies. I think this is an area where kind of everyone's just looked at this and gone, what are we looking at, right? Like, and the whole community is just going to get stuck into this immediately, and there's just going to be a huge leap in what we can do, again, by having this huge wavelength coverage for the first time. And just by looking at these, kind of comparing them immediately, you can start to pick things out that people will already be, I'm sure, writing proposals for ground-based telescopes to try and follow things up. And it's just going to catalyze a whole chain of lots of papers in the coming weeks.
It's been mentioned a couple of times, but we don't know what we don't know yet. And I think it's true that every time we launch a revolutionary instrument into space, like Hubble, we learn things that completely surprise us, that do cause us to sort of change our fundamental understanding of how the universe works. And of course, dark energy is like our generation's example of that. Who called for that, right? Nobody expected that. And we still don't know what it is. There's still so much work to do for that. But I think the point is that it was totally unexpected. And so it's hard to imagine what we might learn with this 100 times more powerful instrument that we really don't know yet. So I think that's definitely possible.
Maybe add something to the planets and the habitability and the questions of that. So one of the big questions I have, right, this goes to Webb being able to better understand the zoo of exoplanets. When you say we're looking for habitable planets, are we looking for planets just like the Earth around a solar-type star orbiting at 1 AU and the star is 5 billion years old? Or is most sort of the habitable area of the universe, is that in a completely different place? Right? Is that planets around much smaller stars, which may be much more common than planets around solar-type stars, just because the smaller stars, M dwarfs, are much more common? Or is most life in moon systems around giant planets, right? So if we have in our own solar system, we have ocean worlds. Is that where most areas of habitability exist in the universe? We just don't know the answer to that, and I think Webb, in this exoplanet research, will be able to make leaps in that direction. We get a much better understanding of where we actually ought to look, whether it should look like the Earth or look like something else.
Other questions in the room? Anyone who? Here we go. Do we have any? We've already asked. We have a couple over here. Oh, and what from some who maybe haven't asked one as well over here.
Hi, my name is Abdul Dramali. I'm with NASA Social. I'm an astrophotographer. That's way better than my work, I admit. My question, we briefly touched on dark energy in the previous question, but my question is more specific to dark matter. And given that we have no instruments that can directly interact with or measure dark matter, can we expect to learn anything new about the makeup of galaxies and other celestial objects in relation to dark matter from Webb?
Field. Actually, no, keep this one. This is good. All right, so the reason that those arcs are there, the reason that those twisty, those long, stretched out, distorted taffy galaxies look like that is dark matter, right? It's the gravity of the cluster that's doing all the distortion, and almost all of that is due to dark matter, right? So of the mass energy budget of the universe, we understand 4%, right? The stuff that's the periodic table, the stuff like us. And the rest is dark energy, which we don't understand, and dark matter, which we don't understand. So, when you look at an image like this, you're right, we can't directly detect dark matter, right? It's confounding, but we see its impact, right? It's the dark matter that is doing the lensing in this field. Right, so there's not enough mass from the stuff we're made of in there to do it. There's not enough stars. It's dark matter. So directly detecting it is something different. That's a laboratory experiment. But what we can do is see how it works and how it interacts. We can see its effects in action, right? So by studying clusters like this, This is what I do for a living, so I'm getting pretty excited. So we can map out where the mass is in the cluster, and we can understand the mass distribution and how it relates to galaxies, which helps us understand where the dark matter is. And that's an indirect way to get at what the heck is going on with dark matter. But it's the most powerful tool we have astrophysically to do that, is this type of lensing experiment.
And dark matter also it's one of the big overarching questions we're hoping to answer with this telescope is really to learn more about the big picture of how galaxies change over time. Right, you see the very distant galaxies in these images look totally different than the way nearby local galaxies look. And sort of putting together that picture of how galaxies change, really important. And we know that dark matter has to have a key role in that because we know all the galaxies that we see are surrounded by this dark matter. Dark matter is sort of the scaffolding of the universe that galaxies sit on. And so this process of how galaxies change over time has to be due really critically to how the dark matter works in the universe. And so even just by studying that overall process of galaxy evolution, we're going to be able to learn more about how dark matter works.
Thank you. And we have time for maybe one or two more questions here, and I know there are a couple over here.
Hello, I'm Elle Joy. I'm a guest of the NASA Social and host of Sunday Civics. It was said in the program earlier, and I know this from different missions, that there's a lot of science and invention that went into developing. And then also from missions and NASA work in general, there are a lot of things that transfer over from space and science to the regular world. And so can you talk a bit about, I know there's one thing so far that has transferred in terms of LASIK surgery or something, but what other things could we expect or look at that could come to the regular world or to regular people from NASA science and missions?
I can start off with one. So you mentioned the LASIK device, and that came from how we had to measure our mirror segments, the accuracy. We had to measure the surface of those, and that turned into a commercial product. There are some other products and processes that were invented within industry that changed how they did business. And so this might not be something that shows up in your optometrist's office or on your kitchen table, but a whole industry learned a new way to bond materials together, to glue composite structures together. And so a lot of invention we may not see directly here in the room, but it changes how industry works. And that's one that was a big one for us. And the company that invented that. And I know folks at Northrop Grumman also had to invent some new processes in their own manufacturing of space vehicles. So that's a big part of this turning NASA research into regular industry products.
Thank you. And this is the last question that we have time for, so we can go ahead with one more up here.
Can you, is it on? Sorry. Okay, sorry. Catherine Troach with NASA Social. You said that the data will be available for astronomers, citizen scientists. Will we have an opportunity to play with some of the data? Will there be projects like the Cloud Spotting on Mars project that's happening on Zooniverse right now?
I should have specified. So I made the mistake, so let me fix it. Yes, anyone can download the data if it's. Some of the data have a period where they're up to a year period where the team that proposed it gets a head start, and then it goes public. But anyone in the world can download the data, so I should have specified. So you're asking about in particular programs that will involve citizen science where they'll have higher. So those presumably are going to kick off, but we need data first. Right, so let's get the data flowing, and then there's going to be lots of opportunities, right? I mean, for one thing, look how many galaxies are in these fields. If you pull up, can we pull up Stefan's quintet? For me, what was surprising about Stefan's quintet was just how many galaxies are in the background, right? Everywhere is a deep field, and that's been true since the first focus images got photobombed, right? Like it's just they're always there. So there've got to be some really cool. And one of the funny things about galaxy classification is humans do it better both galaxy classification and finding lens galaxies. Humans are better at that than machines. In fact, we use the humans to try to teach the machines how to do it, but we're better at it. So there's got to be some fun things and important things for humans are better at classifying galaxies, finding arcs, finding weird stuff, right? I mean, we saw that for the Sloan Digital Sky Survey, that many of the most interesting discoveries, like the green peas, were found by amateurs who were doing citizen science. And we're like, what is that? You know, why is it this little green thing? Oh, that's a galaxy that's pouring out emission lines, like the galaxy we saw at high redshift, right? So there's got to be lots of opportunities for that, just because there's so much data.
Great, thank you, Jane. And as mentioned, that is all the time we have today. But if you had a question that we didn't get to, we encourage you to reach out to us on NASA's media team, and we'll be happy to help. So thank you very much again to all of our panelists today, as well as to those who joined us here and all around the world to celebrate this release of the first full-color images and data from Webb. And as many have mentioned, this is really only the beginning for the mission. So we'd encourage you to continue to follow along. You can find news updates at nasa.gov/web, as well as on social media, Twitter, Instagram, and Facebook at NASA Webb. So thank you all again. And with that, for those watching online, let's take one more look at Webb's first full-color images. Thanks.